What we're going to do is that I'm going to talk about embedded system and how the embedded system can actually be used or are used, and the overview of the lessons, and then eventually I will look at the MX20 board and MPLabX software development tools and so on. So if you look at the overview of the system, we're going to talk about embedded system. Then we're going to talk about microprocessors and microcontrollers, development processes, PIC introduction, and look at the architecture of PIC32, which is a 32-bit microprocessor, and some of the instruction sets and the programmer's models and so on. So if you look at it, then we want to know, it says, what is an embedded system? So embedded system basically is a product which is controlled by a computer inside of it, but it's not basically computer the way as you visualize it, like a desktop or a laptop. However, it's actually got a microprocessor or a microcontroller which actually then control the functionality of the product. And these products, for example, you can have, look at the washing machine, you can look at the car engine management system, for example, dishwashers, microwaves, and so on, mobile phone. So they're all basically can be classified as embedded system because they have a computer or a microcontroller inside them, which actually then controls the functionality of that product. So if you look at this one, normally you've got a microcontroller. Basically it's an embedded computer, and it's got some input, and it's got some user interface, and it's got some time, and it's got some output, and it's got some attached to some hardware and so on then. So for example, if you relate to this one to a desktop or a laptop computer, for example, you could say your input could be your keyboard or mouse. That's your input. Your output, for example, could be your monitor or speakers and so on then. And a user interface, for example, you could actually have software packages and so on then, or the menu which can actually help you to do things and so on then. And other hardware, which is basically, it could be memory, USB, and so on then. So these are basically is classified as an embedded system, which is basically got some sort of input, output, user interface, and some hardware connections and so on them. So if you look at this one, this is an example of an embedded system. So if you look at it on the left hand side, you've got some inputs, which is, for example, the input could be keypad, but in case of a computer it could be actually keyboard and so on then. Then you've got some coin counters. For example, this could be used either in a car park or, for example, one vending machine if you want to actually purchase a product, or if you want to actually enter or exit the car park. It's got gate position sensors, so it's got some sort of sensors that you can actually monitor in order to control the gate. It's got output, so on the other side, right hand side, it's got the output, which is basically called gate actuator, which can basically energize the motors and then open or closes the gates and so on then. The liquid crystal display is basically, could be the same as, for example, monitor. Is the actual display that basically gives you the information, and it's a user interface. For example, you can select the option or cancel options and so on then. So if you look at it, then for example, the one underneath that is mobile communication module. This could be like, for example, Ethernet or internet connection, that basically if you're actually monitoring and controlling it remotely and so on then. So this is an embedded example of embedded system. And the middle is basically a microcontroller or a microprocessor which actually controls it. So if you actually go a bit further than, look at this one. It's a microprocessor and microcontroller. If you look at this one, for example, on the left hand side, you've got the outside world. So basically, this is how interface to the outside world, where the microprocessor or computer is input and output. So you classified anything which is basically keyboard, USB could be input and output, and mouse could be for example input, any sensors you've got that you want to monitor and so on then. So basically you've got input and output in here, so that's the input output basically interfaces for the microprocessor. Then you've got the main core of the microcontroller or microprocessor, which is the central processor unit, is classified as CPU, and it's got some arithmetic logic unit which does all the maths calculation, and it's got some control in here, which is basically, we can go into details later on and so on then. And top of it is basically any stuff you've got, it's got to have some data memory. So for example, you've got RAM or ROM, and if you know, RAM is basically random access memory and ROM is read-only memory, which is basically your program could go in here. However, on the new technology, instead of read-only memory, they use flash technology that basically you can program it and reprogram it and so on then. So this is basically the core of a microprocessor and a microcontroller of an embedded system. So if you look at then here, the architecture of a microcontroller, microprocessor is that, if you can see, you've got in here, this one is the actual internal data bus and address bus. So the data bus and address bus basically is like DHL and post office. So anything is got to have a unique address and a unique postcode, for example, to actually, so the post office or DHL can actually deliver it. And it's exactly the same agriculture, same technology is used for microcomputers and so on. And for example, if you look at this one, it's got program memory, it's got data memory, it's got some digital input output, it's got some analog input output. This is counters and timers, which is basically to use for any timing and so on then. So basically it will have core, plus memory plus peripherals. So you can actually have, to see this one is actually constitute the whole microcontrollers and so on then. So if you look at the, for example, example of peripherals, the peripherals in here, for example, it could be any sensors. It could be like, for example, motion, heat, light, etc., etc., etc. For example, we could have accelerometer, potentiometer, buttons, switches, microphones, and so on then. In here, for example, is we've got Zigbee, we've got Wi-Fi, and we've got GSM phone. So these are, they can actually be used. Normally we use basically Wi-Fi, GSM or Zigbee that can be used with MX20 board to actually develop some software and monitor and control things. So for example, if you look at the outputs of embedded system, you can actually have actuator, which is basically motors and so on. You've got LEDs, you've got basically light emitting diodes and liquid crystal display, LCDs and speakers and Zigbees and so on then. So these are the example of peripherals that you can have and so on them. Now, if you look at it on here, for example, this is what we see. So when you wake up, you go outside and you look at things, you can see cloud, you can see sun, sky, mountain, water, people, and so on then. But if you look at this side, this is what the actual CPU, central processor unit, or microprocessor, microcontroller can see. It's all is numbers. Numbers could be in binary or hexadecimal. This is how the program is written, and is basically developed and can be run by the microprocessors and so on then. So in here we've got to basically write the program and convert it into suitable format that can be used by the microprocessor and so on then. So if you look at this one in here, we're talking about development cycle. Now basically anything you want to do, which is going to be hardware and software, especially if you're writing code for any application or writing code for your assignments and whatever, normally these are the steps you've got to go through. For example, you start with, you revise your source code. Basically, the first stage before that normally is design. You need to actually sit there and design your product and your source code and software to a specific specification to decide what you want to do with it and so on. Then you need basically to convert this one into a suitable format that you can actually download it into your computer or microprocessor and run it. So that's basically, we've got to do the next stage. This one is the simulation. So you can actually simulate it sometimes without the hardware, and you can test your software, especially if you've developed it on a desktop or a laptop and whatever. You can then basically simulate the software and then basically go back and so on. Then eventually you download it with appropriate tools and so on then into your target system, which is your embedded system, and then you actually test your hardware. Okay, so this is the basically development cycle. You go there, and then if there is a problem, what you need to do, you go back and you actually debug it again. So this is basically, you write the software, revise it, compile it, simulate it, download it, and test it. If it doesn't work, you just keep going back until you actually fix it. These are called fixing the bugs and so on then. So basically the program we'll be using for this one is going to be based on C, C++, and assembler as well. So we can actually use assembler and so on then. So the assembler basically was the first language which was developed for actually writing application for a microprocessor, microcontroller, and assembler is very good as long as it's basically the program is small and you want to write device drivers and so on. Then, however, if your application software, your program becomes too large and too big, it becomes very inefficient and it's very difficult to debug it and test it and so on then, because it's virtually at the machine level and so on then. And also the other problem with it is that it's not portable. So that means if you want to change your microprocessor or embedded system and use a different manufacturer, then you have to rewrite everything and use assembler for that particular microprocessor. However, if you actually develop a program which is a high-level language in C or C++, basically you can actually port it. So C and C++ is like basically writing a program in English. Text, obviously you've got to actually comply with the format, and then you can actually develop your software and download it into your target and test it. And it's much easier to actually write program, complicated program, using C and C++. However, you actually need to know as a basic understanding of the assembly language as well, so how you can actually use it and so on then. So if you actually then move on in here, so we looked at it so far. Basically we looked at the microprocessor and how it can be used. We looked at the embedded system, we looked at the development cycle, and now we're going to basically look at MX20 board and how we can actually use MX20 board to use and develop software for it, and then basically test various products and various applications and so on then. So we can actually develop some software application for it. So if you look at this one, normally PIC32 is a microchip 32-bit microcontroller. It's on top of the range. As you know, it's 32 bits. You can actually have microprocessor as 8 bits, 16 bits, or 32 bits. And they are normally very fast. This one, for example, run up to 80 megahertz. However, this one, 80 megahertz, you only need to actually have a clock for about 8 megahertz, and it's got what they call phase lock loop, and then it actually multiplies and increases the speed and so on then. And also if you look at this one, for example, This is the internal architecture of it. It's got the bus matrix, peripheral bus, and it's got various things like UART and I2C, real-time clock, and CAN bus, USB, and so on. Then, so as you can see, this is the internal architecture of a PIC32. It has about half a gig, 512 kilobytes of flash. That's the program that you can actually use. It's got 128K of static RAM, so you can actually use that one there. It's got various cache to actually speed everything up and so on then. And you can actually have USB, Ethernet, CAN bus. CAN bus is basically a serial communication device that can actually normally use in automation, and it's very basically designed for very harsh and noisy environment and so on then. So if you look at all of these one in here, then we can actually then, for example, look at the next slides to see what we've got. This is basically internal architecture of a PIC processor. So what we've got in here, you've got, for example, this one has got port. Now port is basically, as you can see, the arrows are basically in both ways. So it goes to the left and right. That means its input and output is bidirectional. So port is basically a number of basically input output grouped together to actually act as an input or output for a microprocessor. So this is how the microcontroller or microprocessor can actually interface with the outside world. So it's got in here, for example, port A. So you can actually use port A, port B, port C, port D, port E, port A, F, and so on then. So as you can see, these are ports. So what you do, you identify which port you want to actually write and which bit. Normally the ports could be about 8 bits. So you can actually identify any bits within the port and basically either write to it or read from it. Say, for example, as an example, I could actually connect an LED to a port A bit 0. So basically then I can actually then configure that port A bit 0 to have all output, and then I can actually then turn that output on and off. So I can actually flash an LED. So that's another very simple example. Another example is that basically I can use, for example, port B as an input. If I connect a switch to port B, bit 1 as a switch, so the microprocessor can actually configure it as an input, and then basically whenever you change or toggle the switch or whatever, it will detect it. So you can actually use it for any application to start something, stop something, and so on then. So these are the ports. Basically any microprocessor, microcontroller has got different number of ports, depends on the basically the manufacturer and the model number and so on then. And also on these one, for example, you've got various timers, I2C, and so on then. The timers, basically you can actually use that one to time anything you want. You can actually use one of the timer, for example, write a real-time operating system, or use a timer to time things on and off and so on then. So it's got various information that you can actually use and so on then. So that's the internal architecture of a microprocessor and so on then. So we looked at it. So if you look at these one, as I say, the microprocessor, microcontroller, it's got a number of components and are all basically now embedded in one IC. Before, microprocessor basically had just the CPU. If you wanted any input, output like RAM, ROM, if you wanted ports or whatever, they were basically external ICs. So you had to purchase these separately and then basically design them, design your hardware, and then connect them through the bus, serial bus, parallel bus, and whatever. However, as an embedded system, and a microcontroller. Nowadays the technology is moved on, so everything is basically placed on one IC. Another one is that, for example, these are normally analog to digital. So basically what you've got digital input and output, and some of the port can be like analog input. So if you want to monitor the temperature in a room, for example, it's a voltage. Analog is like, for example, a sine wave is an analog. Digital is basically, it's a binary one, which could be like, for example, 1 or 0 and so on. So this is basically the internal architecture of a PIC processor. And you can actually look at the information, more details, get the information from the manufacturers, have a look at the data sheet, and it gives you all the information you record and so on. Now, if you look at this one now, we've got, these are basically what's called reduced instruction set computer. So basically one approach was that with the CPU, central processor unit, and a microcontroller and so on then, was to basically keep things simple and then have a limited instruction set. So that's basically just keep everything simple and have limited instructions. So that's called basically RISC approach, which is reduced instruction set computer. And this one differs from the complex instruction set computer. Complex instruction set computer, they were the original one, and it used to take a number of times to actually go backwards and forwards to actually do something. So for example, if you wanted to actually get something, like multiply it and store it into a memory, so basically it was like fetching, do some maths with it, and then store it away. Some basically microcontroller, the original one, it could take about few bus cycle to actually get the information. They had to set up the address and then get the information data from it, and then basically do something and then set up the address and put it away. However, with the reduced instruction set, virtually everything is done with one cycle, bus cycle. So which makes it really, really fast and whatever. So basically, each instruction is contained with a single binary word, and every instruction normally takes the same amount of time to execute. This allows basically other useful computer design features to be implemented. Okay, and one of the examples is pipelining. So basically that means while instruction is being executed, normally other instruction in the pipeline ready to be fetched from the memory and put in the pipe next for executions and so on. Because normally microprocessor basically does one instruction at a time and so on. However, it does it extremely fast. For example, some of the microprocessor, you can get it at 40 MIPS. That's basically 40 MIPS, which is 40 million instructions per second, which is really fast and so on. So we look at this one. This one is a MX20 development board. So as you can see, this is a PCB board, and it's got various components and so on then that can be fitted and used for all different wireless application, wire and wireless applications and so on then. And here we have, for example, if you look at this MX20 microcontroller based on 32-bit PIC processor, and this is PIC32 MX795F512L. Okay, this one has got basically 6 digital input output, 4 analog inputs, 8 MHz crystal, USB connection, or RS-232. RS-232 is an industry standard. It's been around since 60s, and is still heavily used in industry for automations and so on. So basically you can actually have that one for any serial communication, the same as USB. ICSP header for programming, so basically you could actually use a programming device to actually program MX20. Simply basically you connect MX20 board in here with a PIC3 and a USB cable, and then you can actually download your program into the flash and run it. So if you look at the basically overview of MX20, it's a microcontroller. The processor is using is PIC32 MX795F512L. So it's got 512K of flash, 128K of RAM, and it's operating at 3.3 volts. Maximum supply voltage, basically you can actually use a power supply to power it from 5 to 12 volts. Normally I would suggest if you're actually using the GSM option, use the 12 volts power supply. It's got digital input output, which is basically 6. Also it's got 2 relays. So the relays, if you know, basically if you've got devices which basically needs more voltage to control, like a fan or a light or something, you can actually use 2 relays to actually feed these devices and control these devices and so on. It's an 8 megahertz clock, and it's got basically various options of wireless one GSM GPRS module that you can actually fit in there and then use it as a mobile phone. And then you can actually, for example, use your mobile phone and send the text to MX20, and then you can turn the lights on and off, or you can actually monitor and it will automatically text a message back to your mobile phone. So you can actually remotely, using your mobile phone or Wi-Fi or Zigbee, to control devices and so on. Okay, and also on top of that, it's got hardwired internet connection, which uses RJ45. These are the normal socket you've got on the wall, which is basically you plug in your internet into your desktop and laptop and so on. Now, the main thing we're going to use is that basically the development tools called MPLab X. This is a free software from Microchip. Now, all the software basically we need for developing applications and so on for microprocessor is basically used based on development tools, basically MPLab X. Now, what we've got to do is download all of these one. You can download it from Microchip and on your PC or a laptop, and then basically I'll show you later on how to actually produce, create a new project and compile and download your listing. So if you look at it, and here, for example, these are the application of basically how the compiler and assembler and the linker can be used. The compiler and assembler is basically picks up your source code, either the source code which is you've developed in C or C++, or the assembler, you've done it. So basically it will compile all of these one. The linker job is basically if you've got more than one file, which is normally the case for any project, it actually links all the files and makes sure all the external are actually resolved, all the external parameters and whatever, and everything is basically linked together. If everything is linked together correctly, then the program will be downloaded into your target and so on then. So how do we actually then create a project in MPLab X? So this one, so we're just basically going through the basically the process of how to create in a project using MPLab X. By the way, the MPLab X at the moment is changing all the time, so there are various versions of it, but however the actual concept should be exactly the same and so on. So what you do is that basically when you actually open the MPLab X, this is the actual screen you get. So you've got the overall screen of MPLab X. Normally you've got file, edit, view, and so on then. So when you actually create the new one, you bring up the software and then you basically go to file, and then in here you go to new project. So if you go to file, new project, this is how you can actually then start. Once you've actually then created the project, then you use the option of open project. So you can actually go in here and open the projects and so on then. So these are the various stuff. This is the import. If you need to actually, you had some legacy software based on old MP Lab X and so on, then you could actually import them and so on. Also you can actually export them for various applications and so on then. So you click in here, go to new projects, and when you actually go to new project, this is the screen you'll see, and you can actually go into embedded system. So you go to the samples. So in here you go to the actual embedded system to create the new project. Depends on the actual project itself and so on then. So this one you do it, you go to the embedded system. In here you pick up PIC32 template, PIC32 C template. This is the actual C programming. You could actually, if you look at that one, is C+, underneath that one is C+ template. So you could actually create a template for your project, and either in C or C++. So I would just suggest you actually start with C programming and so on. I've also got various example of assembler that you'll see in various lessons and whatever that you can actually use and so on. So once you've done that, then it will come up with this screen, and in here basically you've got to select your project, and then you can actually then decide where is going to be the location of your project, and then basically the folder for it and so on then. So you've got to actually make sure you check anything. If you're not happy, use the browser to actually browse to the appropriate location and folder, and then basically you click finish, and then it will then basically create the project. So you go there and then fill up all the parameters and so on then, and then that way once you've done it, for example in here I just created a PIC32 C template 1. This is the project, so it will automatically create all these folders in here. So all the folders automatically created. If you look at this one, this is the header files. Now the header files for C is .h in order to actually simplify the program, but the main thing you are interested is source files. So if you go to source files in here, it creates a number of files. It doesn't mean that you need to actually use all of them. However, the main entry to any C programming is main.c. So this is main.c. So that's what you need to actually go in there and then put your software or application in there. Okay, so thank you for listening. So this is basically was the overall view of an embedded system using MX20 board, and then how to actually use MP Lab X in order to actually create a project and download it and so on then. So I will teach you how to actually then download the information into PIC3 using PIC3 and MX20. Thank you. Bye.